Welcome back. Next, let's investigate development of electricity use for lighting. About 3% of global energy use in residential buildings is used for lighting, and in non-residential buildings, this adds up to almost 40% of final energy consumption. Let's start with an overview of available options to reduce electricity demand for lighting. First, we have technical options to increase efficiency of lighting. On the other hand, we have options to reduce the time of use of lighting, like presence control, meaning the light switches on/off depending on the presence of people in a room, daylight control, intensity of lighting responds to the amount of daylight, and finally good habits, like turning the lights off when you leave a room. Let's start with lighting efficiency. First, we need to define the efficiency of lighting. Energy efficiency is defined as input of energy divided by useful output. Useful output for lighting is expressed in lumen. This is the total amount of visible light that a light source emits in all directions. Efficiency of a light source can therefore be expressed as the amount of lumen delivered per watt. This slide depicts the historical development of commonly applied light sources and their efficiencies. Starting with a candle with an efficiency of 0.1 lumen per watt and a lifespan of only a handful of hours. Next, incandescent lamps were introduced, which are 100 times more efficient and have a lifetime span of approximately 1000 hours. Next, halogen lighting was introduced with slightly higher efficiency but with a 5-fold lifespan. This was followed by compact fluorescent lighting, CFLs, entering the market with even higher efficiencies and lifespans. Finally, most recently, LED, light-emitting diodes, came on the market with a further doubling of the efficiency and lifespans compared to CFLs. This table shows the enormous increase in efficiency of lighting that has been achieved over the last decades. This is further illustrated in this graph showing the achieved improvements in energy efficiency over the last decade and expected efficiency improvements up to 2030 for lighting technologies still in use that include LED, linear fluorescent, compact fluorescent, halogen, and incandescent lighting. The picture shows that the efficiency of LED has more than doubled, while efficiency of the other lighting technologies hardly improved. This is resulting from the fact that investments in energy efficiency improvements are targeted at LED technology, which is rapidly dominating the lighting market. That is depicted in this graph showing the development of the global sales by type of lighting. It can be observed that efficient LED lighting is quickly expected to dominate the market. LED sales now appear to have overtaken fluorescent purchases for both residential and commercial applications, and the LED share is expected to continue expanding while other types of lighting will gradually disappear from the market. So far, we investigated the technical efficiency potential to reduce electricity consumption for lighting. What about the potential to reduce time in use, like good habits, presence and daylight control? Start with the first one. Good habits include that you turn off the lights when you are leaving a room or don't use more lights than needed. What we know from research that efficiency improvements in lighting are partly offset by the fact that people tend to use more light or don't turn it off when they know they are using efficient technologies. This is not typically for lighting, but is also observed with other technologies. Finally, let's look into two examples to illustrate the potential for lighting efficiency combined with presence and/or daylight control. In non-residential buildings like supermarkets and shops, education buildings, offices and hospitals, the use of LED lighting in new buildings and where lighting needs to be replaced is already the standard. This has led to significant reductions in electricity use for lighting. According to the IEA, Another 20% can be saved in 2040 on electricity consumption for lighting by reducing time of use of lighting by applying smart sensors and digital controls that detect the amount of daylight and adjust illuminance of lighting accordingly. So far, we investigated the electricity use for lighting in buildings. But when you work for a local or regional government and are developing plans to become climate neutral, you might want to investigate electricity use for street lighting. For example, in the US, street lighting is often the first or second largest source of energy use for local governments, typically accounting for 25 to 50% of the municipal energy bill. For the EU, this is estimated to be about 20%. This means that investments in more efficient smart lighting, energy-efficient LEDs combined with smart sensors that can detect presence and the amount of daylight offer an opportunity to save on government spending and contribute to the reduction of CO2 emissions. Energy savings of 50 to 70% are reported from European cities, and those savings go beyond savings on just the electricity bill, because we have seen that the lifespan of LED lighting is much longer than for conventional lights, implying a lower replacement pace and less need for repairs, turning this into an attractive business case. Thank you for watching this video. In the next video, we will look into potential to save energy by smart use of available data.